Hello and welcome to this YouTube series on Calculus 1. In this class, we'll be learning topics that are covered in just about any university level Calculus 1 class. And yeah, let's start. So, the first topic is limits. And this is a very important concept that's used just about everywhere in calculus, from Calc 1 to Calc 4. And yeah, they're very important to understand properly because without them, you can't really get anywhere. And just as a disclaimer, I hope you have a good working knowledge of pre-calculus or algebra 2, essentially, because I'm not going to cover that. I'm assuming you have a good knowledge of that. All right. So, what is a limit? That's what we're going to learn today, and we're going to discuss how we can get the rate of change of a function, as well as the slope of the line tangent to the graph of a function using various techniques. In addition, we'll learn the idea of continuity and the intermediate value theorem, and we'll eventually learn the actual definition of a limit. Apologies if I sound a little rattled. This is my first time doing anything like this, so I'm very much winging it right now. All right. So, the most important concept for understanding limits is, first of all, understanding what you're really solving for. And when you're usually getting a limit, it's first of all important to understand what's called a tangent line and other general rates of change. Though that's pretty important overall to understand what we're talking about here. All right, first let's understand the idea of tangent lines. So we can imagine a graph, let's say, that looks like this. Something like that. So, you might have learned this before, but a tangent line really is just a point that touches the graph at one point and one point only. So let's say we want to find the tangent line here at this, whatever this point is. The tangent line is going to be vaguely something like that. So you have your tangent line here, and that is unique only to that point on the graph. It's not equal to that anywhere else. And yeah, that's basically the idea of a tangent line. It's not tangent here. It's not tangent anywhere else. All right. Let's see. All right, with that knowledge now, let us try to find the seat tangent line for this function. All right, so you might be wondering how we're going to find the tangent line here. You only have one point, and as you might know, the formula for slope and is just change in y over change in x. Sorry. Right, so you might be wondering how you can get this from just x equals 1. First of all, let's first start with what we know. We know what x of 1 is, f of x of 1, f of 1, sorry. So your points are 1, f of 1. And for this function, I believe, sorry, this doesn't make much sense, 2x squared. So your point's going to be 1 comma 13. Right, and now what we can do is plug in to our main function here, our slope function, which you might know as rise over run or anything else. So it's going to be m equals your so it's y final really minus 13 divided by x final minus 1. So this is what we have here. And now with this, we can find what's essentially the secant line, which is basically this line here, because it intersects 2 points on a graph, and that means it's a secant line. So now we can solve for the slope of the secant line just by plugging in any other points that are on the graph. So just to be friendly, let's plug in f of 2 and 2, like that. And I believe, if my calculations are correct, it should be giving 2, 7. Right? Yes. So now we can plug 2, 7 into our secant line slope function. So now it's really just 7 minus 13 over 2 minus 1. That gives you a slope of negative 6. So for the graph of 15 minus 2x squared, the tangent line at x equals 1 has to be vaguely close to negative 6 in some way, shape, or form. And this is a pretty good approximation if you're not interested in accuracy, for just getting an approximation or something. But if you want to solve the actual tangent line, there's some other ways. What you could do is really take another value that's now in between 1 and 2, say 1.5, right? That gets closer to the actual estimate, the actual value. And that's the general idea of limits, really. So what we're essentially then now doing is, let's imagine this to be the graph of 15 minus 2x squared. Say this is our 15 or something, I don't know. Say it's that. Let's say this is x equals 1. Here. And we want to find the actual slope. But what we've done right now is for x equals 2 over here. And if you draw the line between them, that is not a very good line. 1 second. There we go. Yeah. See, we've drawn the line between them like that. And what we can do, basically, if you take the slope of at 1.5, what we're now doing is basically creating a secant line here, but that's closer to 1, which is what we're really interested in. Similar, we can just keep going like this. Approximately like that. And you can keep going infinitely closer. You can keep getting infinitely close to x equals 1. And all of your approximations would be getting infinitely closer. And obviously there's a lot of ways to do this. We could make a table. You could use your good old graphing calculator to solve for this. But yeah, you can get it that way. All right. So with that knowledge, let's see if we can come up with a general formula that lets us just plug in any x value we want and find the approximate slope of a secant line. So as you might remember, let's first call our original point P, and this one Q, just for namesake, right? So for solving for MPQ, you would remember that it's just f of x. You can set it as f of x minus f of 1, because that's what we're solving for, x minus 1. So now what you can do is just plug in your numbers, which is pretty straightforward. So 15 minus 2x squared minus 13 over x minus 1. And when you simplify all of that, you get 2 minus 2x squared over x minus 1. That's pretty easy to understand. So, with this formula now, right, let's see if you can make like a handmade table of values. I'm not sure how to project a screen from a TI-84, so I'm just going to hand draw this. So, let's see. Alright, welcome back. I probably would have edited this out, but what I've essentially done is I've created this table. It's a pretty simple table to explain. So this column is for values that are greater than 1, and this table here for x values is for values that are less than 1. And that'll make sense in a little bit in a few more videos, I think. So with this, let's see. We want to keep plugging in values that are getting ever so closer to 1. And how we can do that is not just plug in 5, 4, 3, 2, 1, not like that, but values like 2, 1.5, 1.1, 1.01, 1.001, and so on. And similarly, the same logic applies for the other column here. So you can plug in 0, and this time we're getting closer to 1, so we have to get, the 0 has to increase now. So 0, 0.5, for example, 0.9, 0.99, 0.999, and so on and so forth. So, let's see, we already solved for MPQ at 2, which is -6, right? And then for these, I'm pretty sure you just have to plug into a calculator unless you're some kind of human calculator. So yeah, if you plug into a calculator into your graphing calculator, you can just get a table like this for whatever interval and whatever. But I'm just going to plug into my calculator over to the side. So this is 1.5, MPQ is -5. For 1.1, it's -4.2, then 4.02, -4.002, and so on and so forth. For the other side, we haven't solved for any of it, so we're going to do this together, I guess. So MPQ at x equals 0, well, you can just plug in here. It's just going to be -2. Right? Yep. Then -3 for -0.5, -3.8, -3.98, negative 3.998, so on and so forth. As you can probably tell just from this table alone, while we don't have an actual number, you can kind of infer that the slope at x equals 1, it's approaching the value of negative 4, right? And that's what we just solved here. You can see it's getting closer and closer to negative 4 from this side of the graph. I'll go back to my main graph here. You can see from this side, as we approach negative 1, negative 1 like this, we are getting closer and closer to the slope of negative 4. And as we come from this side, we're also getting closer to negative 4 as inferenced by our table. Or I guess derived from our table, that's probably a better way to say it. So this really means that how you would write this now, I guess, is it's like how we would write this in a problem, I guess. You would just write the secant lines of f of x approach m equals negative 4 as x approaches 1. I believe that would be a pretty acceptable response for a question like this on any test, review packet, quiz. What say you? Alright, so if this is your response, that's probably going to be acceptable, like I just said. But in a type of question where if you're asked for the equation of a tangent line, that's also not actually that bad. So you might have learned this in like 9th or 10th grade, assuming you're a person in like 11th or 12th grade taking calculus, that if your line is given by, if your point or your equation of the line going through a point is given by this notation, so you know that your y equals mx plus b basically. So it's really just like this, or really to make it a little easier, just this form here. I'm blanking on this form, but this is the form that a lot of equations are given in. I believe it's called point slope form, sorry. So you're given your equation, right? So f of x equals 15 minus 2x squared. So what you can do is now you can plug in the numbers you were given in your original problem, or really as x approaches 1, that's the only thing you know. Then you can plug into this formula. And the same thing, how to say this sentence in math form, I suppose, is really just y equals f of 1, or 13, minus your slope that you inferred to be negative 4, minus 4, multiplied by x minus 1, or really negative 4x plus 17. So this mathematical sentence is equivalent to this English sentence in this context here. That's not really ever true, but in math it usually is. Okay, with that problem first solved, you just solved your first calculus problem. And yeah, there's a couple of things to notice here. And this is really just one thing, and it's really more of a warning than anything. You might have noticed how the values that we got in our table were pretty tame. They weren't particularly difficult. And there are usually points or functions that aren't so nice, and you'll learn about them more as we progress. And yeah, a lot of times they're not going to be so friendly, and you might require more complex calculations, or the functions would be doing something weird, like they might have an asymptote, they might have a hole, they might be jumping. You'll learn what these are soon, don't worry. And yeah, And so that's why it's important to use a lot of values that are very close to the number you're actually solving for. So you don't want to use, let's say if you're at x equals 1, like I explained before, you don't want to be using x equals 5 for your reference points. You really want to be using, ideally, x equals 1.1, 1.001, 1.0001, and so on like that. That is important to know just for the sake of getting an accurate approximation. Otherwise, you're going to be really far off, and you'll probably get points taken off or something, and nobody wants that, right? So, yeah. All right, so that's there. And another thing to realize is if you ever, for some reason, you solve for this kind of function, you might have noticed if you've taken pre-calculus or something that you really can't have x equals 1. You cannot plug in this x equals 1 into this. That's mainly because your denominator goes to 0. It equals 0, and you can't divide by 0. But that wasn't too much of a problem in this case because we're solving for values around 1 and not at 1. And that's really the important thing about limits. You don't really care about what's happening at 1 or at your point. You're caring for what's happening around that point, that's the important part to understand. Okay, that's tangent lines. And now we're going to go on a slightly different topic that's still very much related to tangent lines because that's the essence of most of calculus. It is the topic of rates of change. And I'll probably, in the description or something, I'll link some problems. I'll make a PDF of them or something. All right, so with rates of change, they're very closely related to tangent lines because they really are. And that's basically just your slope, but instantaneously, I guess. So what we're really always trying to determine in calculus for rates of change is like an instantaneous rate of change, or really just the rate of change at x equals a. And that might be a quantity like the amount of water in a tank after some time, or the distance. That's like your f of x function, and you're trying to find how much water is flowing out at one particular time. Or if your f of x is the distance traveled by the car after some time, you try to find like your speed or something at one particular instance. Obviously, these functions don't really match real life. Like in physics, you'd make ideal assumptions. The functions here, they're also very much assuming ideal conditions. And it's important to know that. So there's always going to be error, obviously, in your calculations compared to real life. But it's always going to get you pretty close. So have no fear. So with that out of the way, we're going to first cover something called average rate of change. And that really, as you might be able to guess, is just your secant line. And the formula for that, as we covered before, is just your change in f of x or change in y over change in a. So really that can be notated as f of b minus f of a over b minus a. Or if you want to be fancy about it and make your own a secant line equation, as I'm going to call it from now on, f of x minus f of a over x minus a. All right, so with this formula, just to estimate rate of change, instantaneous rate of change specifically at x equals a, all you need to do is do the same as we did in the previous problem, is just to solve for values that are getting closer and closer to your actual a value, and keep estimating and computing your values. Not estimating, just computing. So let's look at like an example you might see on like a test or something. This is a pretty standard question as well, actually. So this is good practice for all of you. So let's say you have a hot air balloon, or a normal balloon. Let's make it less wacky. An air balloon. Sorry. Let's say the amount of air in a balloon is given by this function. V of t, that's just volume. 3t cubed minus 6t squared plus 35. So this function represents the air in a balloon after t hours. You can graph this if you'd like, but I don't think it's too important. And the question is, estimate the instantaneous rate of change of the volume after 5 hours. I cannot spell today. So that's your important number there. So how you can go about doing this, as usual, is the same process as we did before. It's just under a different name. It's the same process, different name. I can't figure out how to make that rhyme, sorry. So your average rate of change function is just, as you remember, f of x minus f of a over x minus a, correct? Yeah. So you can just plug in your f of x, or in this case, v of t. So that's t cubed minus 6t squared plus 35. And then f of 5, or v of 5, really. Let me fix that before anyone comments angrily. Yeah, they're just variables. They can have any designation they want. It doesn't matter too much, right? So then, yeah, v of 5 is, I believe, 10, negative 10, or is 10, it's just minusing it, subtracting it, and it's going to be t minus 5. So I'm going to bring this down here. So I believe, if my math is correct, this should simplify to t cubed minus 6t squared plus 25, and over t minus 5. So once again, you're probably going to figure out that you can have this function cannot equal 5, but that doesn't matter again, because that's all, we're not solving for what's happening at t equals 5, we're solving for what's happening around t equals 5. So what we can do now is make that quirky little table from last time, and yeah, derive it from there. I'll see you in a bit. Alright, hello, I've made the table. So what we can do now is, once again, plug in values that get closer and closer to 5 from both sides of 5. So let's start from, for values that are greater than 5. So let's start with 6, 5.5, 5.1, 5.01, 5.001, and just to be really accurate, and just for the fun of it, 5.0001. And I'm pretty sure we're going to get absolutely massacred by this tiny space here, but that's fine. Let's do 4 here on this side for values that are less than 5. 4, 4.5, 4.9, 4.99,
wait, sorry, 4.9, you saw nothing, 4.99, and 4.999. I'm not going to do the other ones. It's fine. This is already more than enough information to calculate, so it should be okay, I think. So your slope at t equals 6 should be 25, then 19.75, 15.91, 15.0901, 15.009001, and I don't have space for this one, so let's just erase that and pretend it never existed. So, yeah. And then for t equals 4 and that group of numbers, it's just 7.0 or 7. That math does not matter here. 10.75, 14.11, 14.9101, 14.9991, and something. I don't have space. All right, so I'll let you guess what number the graph is approaching now, what slope the secant lines are approaching. I'll give you like a second. Okay, second's up. So you can estimate that the rate of change here is 15. God. Right? So how would you say this mathematically? You would probably just say that you'd use the same formula from above, so I'm just going to shamelessly copy and paste that. This one here. Alright, so you have this. So we know that t is 5, or really x equals 5. So it's going to be y equals, let me calculate this out. I forget. Alright, I believe it should be 10 plus 15 times x minus 5. If I'm incorrect, please correct me in the comments later on. Okay, and this is our mathematical answer, but for such problems like this that involve great volumes of air or something, or volumes of water, you want to use the correct what's it called, units. And obviously 15 is just a scalar value, doesn't have anything, and you want to give it units. So you might be familiar with this, but volume is usually units cubed, and for this we're using t as hours, I believe. So our units is going to be centimeters, in this case, cubed per hour. I'm pretty sure. You can just make it anything. I'm just choosing centimeters per hour, but yeah. So in this case, the rate of change at this point is 15 centimeters cubed per hour. So that really means it's like the balloon's inflating or something. I don't really know what you're solving for here. And what you have to be careful for while interpreting this value here is that after an hour, you probably are not going to have 15 centimeters cubed more of air in your balloon, because, as you know, it's a function. It's not a constant, like, amount of air is not being pumped into the balloon. So at this instant in time, you're having 15 centimeters cubed. At t equals 6, you might not have the same amount of air being pumped up. So
imagine it's like a really faulty air pump or something that likes to change its air output periodically. Another type of problem you might come across in
such types of questions is velocity.
and you probably know that velocity is speed with a direction, or as the famous meme that involves vector has magnitude and direction. That's basically velocity, essentially. Okay, so as you know,
Speed in general is just distance over time.
or really, this can translate to average velocity. This is average speed, so therefore, your average velocity, because this time you have numbers, like you have -5 over t or whatever, or something,
You have magnitude now and you have direction. So it's going to be change in position over change in time. Right? So this is just another rehashing of
the secant the secant line secant slope formula, as I like to call it now.
so as usual, this is now really just oops f of t minus f of a over t minus a. And you might have noticed the notation change. That's just so that
It's easier to understand because velocity is very much it's time based. It's not really based in x value or anything. That might be taken for distance or something. So t usually.
stands for time.
All right. Okay, so let's say we have
I don't know, something that's moving at this function. So let's say f of t equals x squared minus 1.
let's say something is moving and its position is given by this function here.
And we want to find its velocity at, sorry about that, t equals, let's say, I don't know, 2. So how would we do this? So we have our function here. We have this
Nice little formula here.
So what we can do is just plug in t squared minus 1 minus f of 2, which is God, why am I doing this? It's 3 minus t minus over t minus 2. So this simplifies to t squared minus 4 over t minus 2. And now what we can do is, with this, we can now just plug in values with the table.
And I'm not going to do this out. You can do this on your own, but give me a second to calculate out. I'm not going to write it out this time.
Okay, so I've done the calculation, and
after you do your tables and everything,
your velocity should be,
what did I write down?
4 units per time. I didn't provide units, so let's just say meters per second because metric is superior, obviously. So if you want to make your tangent line equation or something, you can just make it as y equals 3. God, I'm forgetting the formula. Plus 4 times t minus 2. So that's your mathematical sentence.
And yeah, that's your answer. believe the last thing I'm going to cover in this video is a pretty insignificant but important change in notation. So as you might have noticed now, basically the three problems that we did for the past hour or something, I don't know, has been of this form: f of x minus f of a over x minus a. And this would suggest that these three are really the same problem, and they really are. And we're really working only with changing units, basically. The math is the exact same. And to make it easier to understand in the future, we're just going to do this little change here. So what we're doing is we're solving for what's happening at x equals a, or around x equals a. And to do this, we really just chose another value and plugged it into our equations. Right? Yeah. So how we can determine how far away that value, first of all, is our different value, and then we can define a new point based on that decision. So if we want really like a distance of h, for example, so instead of it now being x equals a, we're now just doing x equals a plus h, and h is like a small increment basically. So let's say, maybe this will make more sense in a number line. Let's try that out. So you have your number line here, and you have your a value, and that's the one you're solving for. And you want to find the limit, the instantaneous rate of change or something. Instead of having different x values here or something, you can just have x equals a plus h on this side, and x equals a plus h here. But the only difference is, for here, h is going to be greater than 0, and for here, h is going to be less than 0. So with this now, what we can do is plug into our secant line formula. So f of x minus f of a over x minus a and now we're going to plug in x equals a plus h. So f times f of a plus h minus f of a over a plus h minus a. So that gives us f of a plus h minus f of a over h. So now this really is just for a specific value of x, i.e. x equals a. Right? So what we can plug in now, we can substitute this x, this a in for x. F of x plus h minus, write that better, over h. So that's going to be our new, I guess, definition, if you will, for now. Okay, yeah, that's it for this video. Thank you for watching. I hope this was helpful. I don't know when the next one will come out, but if you subscribe and hit the notification bell, you'll get a notification when I do. Make sure to follow me at the Math Fella on Instagram. I'll be posting on there as well. And you might see some chemistry and physics videos as well in the next month or so, because why not teach the other important subjects as well, right? So yeah, anyways, thank you for watching, and bye-bye.